Let's look at the process for drawing the graph of a function. The first step is to determine the domain of the function. We want to know the values for which the function is defined. Next, locate the x and y intercepts. This can be helpful in finding a more accurate depiction of the graph. Next, determine the locations of any asymptotes. Determine if there are horizontal asymptotes by finding the limits of f as x approaches positive and negative infinity. If either limit is equal to a constant L, then a horizontal asymptote is located at y equals L. If the limit approaches positive or negative infinity, then check to see if any oblique asymptotes exist. An oblique asymptote may exist if the degree of the numerator of a rational function is greater than the degree of the denominator, and the rational function can be rewritten as the sum of a linear function and a rational function. Vertical asymptotes are located where a rational function does not exist if the limits as x approaches that value approach positive infinity, negative infinity, or positive infinity from one direction and negative infinity from the other. The next step in graphing a function is to calculate the first derivative and use the derivative to find the critical points. Use the critical points to find intervals where the function is increasing and decreasing, and then find any extrema. Next, calculate the second derivative to find any inflection points and where the graph is concave up and concave down. Finally, graph the function using the obtained information. Here we are asked to sketch the graph of f of x equals x cubed minus x squared minus 4x plus 4. The first step in graphing a function is to find where the function is defined, or the domain of f. We have a polynomial function, and polynomials are always defined for all real numbers. Next, let's determine the x and y intercepts. The y-intercept occurs when x equals 0, so let's evaluate the function at 0. Simplifying, we get f of 0 is equal to 4. So the y-intercept is 4, 0. Now let's look at the x-intercepts by setting the function equal to 0 and solving for x. Let's try to factor the polynomial by grouping. In the first two terms, we can factor out an x squared, and we can factor negative 4 out of the third and fourth terms. Removing the common factor, we get the quantity x squared minus 4 times the quantity x minus 1. Notice that the first factor is a difference of two squares. This means that we can factor the polynomial further as the quantity x minus 2 times the quantity x plus 2 times the quantity x minus 1. Setting each factor equal to 0 gives the zeros, and thus the x-intercepts. So our x-intercepts are at negative 2, 0, 1, 0, and 2, 0. The next step in sketching the graph of the function is to determine the asymptotes. Our function is a polynomial, so it won't have any vertical or oblique asymptotes. Let's look for horizontal asymptotes by examining the limit as x approaches positive and negative infinity. We'll find the limit as x approaches positive infinity first. As x gets large, the function approaches positive infinity. Now let's find the limit as x approaches negative infinity. As x gets extremely small, the function approaches negative infinity. Since the infinite limits do not approach a finite number, there is no horizontal asymptote. Next, we'll find the intervals where the function is increasing and where it is decreasing, as well as any local extrema. So we need to find the critical points of f, if there are any. Critical points are the points where the first derivative of f is either equal to 0 or undefined. When we take the derivative of f, we find that f prime of x is equal to 3x squared minus 2x minus 4. The derivative cannot be factored, so we'll need to use the quadratic equation to find the zeros. Substituting for a, b, and c, we get x equals 2 plus or minus the square root of negative 2 squared minus 4 times 3 times negative 4 all over 2 times 3. After simplifying the equation, we find that x is equal to 1 plus or minus the square root of 13 all over 3. Approximating, we get x is approximately equal to negative 0.87 and 1.54. So, we divide the domain into 3 intervals using the critical points. By finding the sign of f prime on each of these intervals, we can determine where f is increasing and where it is decreasing. Notice that f changes from increasing to decreasing at x equals negative 0.87, and f changes from decreasing to increasing at 1.54. This means that there must be a local maximum at negative 0.87 and a local minimum at 1.54. Let's find the y-coordinates of the extrema by substituting each critical point into f. For f of negative 0.87, we get approximately 6.06. For f of 1.54, we get approximately negative 0.88. Therefore, we have a maximum at negative 0.87, 6.06, and a minimum at 1.54, negative 0.88. Now let's determine the concavity of the function. To do so, we need to find the second derivative. When we take the derivative of the first derivative, we get f double prime equals 6x minus 2. This factors as 2 times the quantity 3x minus 1. Inflection points or changes in concavity occur when the second derivative is equal to 0. When we set f double prime equal to 0 and solve for x, we get x equals 1/3. Next, divide the domain into 2 intervals and determine the sign of the second derivative in each interval. Note that f is concave down from negative infinity to 1/3 and concave up from 1/3 to infinity. Here we see everything we know about the polynomial function and its graph. Let's start by plotting a point at 0, 4, the y-intercept. Next we'll plot the 3 x-intercepts. Now we'll plot the points at the local maximum and minimum. Since these values are approximated, you don't have to worry about finding their exact locations. Finally, we'll use the intervals where the function is increasing and decreasing, as well as the concavity to sketch a graph of the function.